Hello, everybody. This is Mr. Boswell. Hopefully, the sound's coming through here because if it's not, I'm wasting my time. But I'm out here in my backyard in nature, um, which is where you usually find your backyard. Okay, so I'm going to try to make a video on how to write formulas for chemical compounds. So I have these devices. I have this little whiteboard. I bought a whole box of these to use. I was going to pass them out. Got these nice little pens here, to go with them. But of course, Mr. Corona has taken care of all of that. And maybe one day we'll be back in the classroom wishing we weren't, which is what we usually do when we're in the classroom. All right, so here's my board. And I'm going to try to switch cameras, which may be a problem. It's going to take a little while for me to get. There's my bush, which the flower bed needs cleaning out. That's not the one I want. And let's switch again. And there we go. There's the whiteboard. So here we have the periodic table. And notice I put some numbers up here. And I'll pause in a few minutes and get back to that and let you copy them down. But for right now, let me just give you a little review. And I think my camera is going to be put on automatic focus here. I'll try just a second. Let's put sodium and chlorine down and see if I can get those in focus. Okay, I think that's good now. Okay, so here is this compound we put on our food, sodium chloride, and let's see what happens to make sodium chloride. Sodium is a silvery metal, looks very much like aluminum, and except for the fact that it's really, really soft, and you have to store it in something like kerosene or mineral oil because it reacts very violently when it gets in contact with water. All right, and then we have chlorine over here. Chlorine is very deadly, poisonous gas. Every once in a while, and some of you have heard me tell this story before, but every once in a while you hear of a train accident and there's a tank of chlorine that's been on the train on the tracks, and maybe it's flipped over for one reason or another. And they will go into neighborhoods in that particular area and clear everybody out because they don't want everybody breathing this horrible, horrible poisonous gas. So when we put them together, these two very dangerous things, sodium could actually be used as an explosive. It's that dangerous, similar to maybe a hand grenade or something if you get enough of it. All right, so what happens to this compound to make it sodium chloride, which we have these salt and pepper shakers with the little holes in them, and we pass this around each other. Somebody says pass the salt. You don't worry about the fact that chlorine's poisonous, and you don't worry about the fact that sodium's an explosive metal. So what happens? What happens between these two? Well, do you remember the rule that we said all atoms are trying to obey the octet rule? Okay, so the octet rule is that rule that says that atoms are trying to get 8 electrons in their outer shell. And when you put electrons into atoms, you can't put more than 8 in the outer shell. So what can we do with these two, or what happens with these two to get them to the point where they have 8 electrons in their outer shells. Well, I'm going to draw this little sodium atom over here, and I'll just use the Bohr model. We have 1s, 2, 2s, 2, 2p, 6. And you won't have to do this with every atom. This is just showing you kind of why atoms end up with charges on them. And so here comes 3s. And this, of course, is where sodium runs out of electrons. Okay, you see where it is over here. It has 11 electrons. And if you count those electrons, you'll see that there's 8 here, 9, 10, and then there's 11. So that's sodium's electron configuration. And then over here, we'll put chlorine. Let's label this sodium. And let me move that nucleus a little to the right here. And we'll draw the shells for the Bohr model, this one as well. We'll draw them coming back the other way. Here's 1s, 2, 2s, 2, 2p, 6. And then here's 3s, 2, and 3p, 5. Okay, so this one we'll label chlorine. All right. Now in this process here, we call a chemical change. Keep this octet rule in mind. It's the octet rule that really governs what happens in most of chemistry. So everybody's trying to get a full outer shell in chemical reactions. And sometimes they can get a full outer shell better with some atoms than they can others. And that's a discussion for another day. But anyway, if you'll notice, let me show you where chlorine is. Chlorine is over here, and that's group 17. And they all have 7 electrons in their outer shell. And you see the 17 there, the atomic number. So many electrons it has, and protons in the nucleus. So the first 2 shells add up to 10, and then you put 7 with it, and that's where the 17 comes in. Okay, that's 17 right there. There we go. All right. So we've got these 2 atoms here, and they're about to react. Deadly explosive over here, poisonous gas. But in something, in each other, if you picture them maybe as people, they see something that they want. Okay. So we end up thinking logically here. Let's think logically. This sodium atom has 1 electron in its outer shell. It wants 8 in its outer shell. So it has 2 choices. It can get 7 electrons from somewhere else, or it can lose that 1 electron. And look what's waiting behind it. 8 electrons. Okay. So it has a choice. It can gain 7 or lose that 1, and it just doesn't make any sense for it to want to gain 7. Besides, its nucleus is not strong enough to do that. Okay, so what happens is this little electron that's located there gets up and transfers over to this atom here. And if we erase the shell, which is no longer there, look what happened. Sodium ended up with a full outer shell. Okay, it has 8 electrons in its outer shell. Okay, now let's go and see what happens over here. The chlorine has the same 2 options. It can get rid of 7 electrons, or it can gain 1 electron. And, it just seems like it makes sense if it gains 1 electron rather than losing 7. And thus, this electron goes into this spot right here. And let's see if I can erase that without causing too much damage. Okay. So there is 3p. It now has 6 electrons in its outer shell. And if you refer back to your 2nd grade arithmetic, you can see that 6 and 2 add up to be 8. All right, so both of those atoms now are different. They're different because they've undergone a chemical change. And when you look at that definition of a chemical change, and it says that atoms take on new characteristics and they've lost their former characteristics, their formal personalities, if you will, then for something to change to a powder that we put on our food, when originally they were both extremely dangerous. Well, that's a perfect chemical change. That's what the definition means by losing old characteristics and taking on new characteristics. All right, so here is now sodium chloride, we call it, or salt. And you know that some of you've heard me say many times that salt is not the only salt. Basically, anything that has a metal in it and a non-metal in it is technically a salt, but that's another discussion for another day. Okay, now, if we look at sodium before it reacted chemically, here's what we have. It has 11 protons and 11 electrons. And chlorine has 17 protons and 17 electrons. Okay, if we add those numerically, taking into consideration the fact that we know these are charges, we can say that this is a negative 17 and this is a positive 17. And that adds up to 0. They really aren't mathematical in nature. They're really electrical in nature. But fortunately for us, they also add up the same way electrically that they do mathematically and cancel each other out. So here we have 11 protons and 11 electrons, and this adds up to 0 over here. But when we take the sodium and we pull that electron off and send it over to chlorine, something happens to this balance here. We now have 11 protons and 10 electrons. Okay, electrically and mathematically, that's going to add up to positive 1. On the other side, we've got 17 protons and 17 electrons. But after chlorine picks up an electron, we have 17 protons and 18 electrons. And numerically and electrically, that adds up to negative 1. So if we took those two charges now and added those together, they would give us 0, which is what we have to get every time we have a chemical change. We have to have the same number of electrons that are lost have to be the same number that are gained, or I should say the electrons that are lost has to be the same number that's gained. All right, so in this abbreviated version of writing formulas, let's just make some generalizations here that we normally would spend more time on. But what's happening here is, notice the zigzag line here which separates the metals from the non-metals. Okay, the metals have positive charges because they are the ones that have less than 4 in their outer shell. And it's easier for them to lose a few electrons than it is to gain a lot of electrons to have a full outer shell. And so it ends up that metals in chemical reactions will be positive. And you can pause this video and get you a periodic table offline if you want to, online, and run it off, and then it's offline. And you can put these charges up there like so. And you can use that when you're writing chemical formulas. Over here on the non-metal side, and once again, there's far more metals. All of these are metals over here. There's far more metals than there are non-metals. But non-metals are the ones that have too many electrons in their outer shell to lose. All right, so it's easier for them to gain a few electrons than it is to lose a lot. So when an atom, let's get back over here, see what happened to sodium. Its electron count went down 1. And so it turns out that when atoms lose electrons, they become positive. And then over here, we see that chlorine gains an electron and it becomes negative. Okay, so when atoms gain electrons, they become negative. When they lose electrons, they become positive. And what makes that happen is, notice, in both cases, the proton number doesn't change. And so when you mess with the electrons, whatever you're doing to the electrons, that's what's going to affect the charge. All right. So if you want to pause this video and take a picture of that, I'm going to do another one here in just a second. Okay. Let me flip this over. See what my little dog wants. She wants me to love her, and I can't do that right now. So she may bark in just a second for me to pick her up, but we will, I'm used to that. I've been teaching teenagers most of my life, and, they bark a lot. So, all right, here we go. Let's review a little bit. The metals are positive, the non-metals are negative. So let's take another element. Let's take an element here, calcium. And then on this side, let's take oxygen and see what happens to them. All right, so here is calcium. And my camera's messing up again. Okay, here's calcium. And here is oxygen. All right, if you look at where they are, you see what these charges are for now. Look where oxygen is. It has a -2 above the column there. And then here's calcium. It's got a +2 above the column. So now all we have to do, now that we know what's happening is electrons are transferring, let's put a +2 here and a -2 here. And remember, like I said, this is electrical in nature. Charges are electrical in nature. However, they add up just like negatives and positives do, or I should say minuses and positives do in arithmetic. All right, so here's my calcium with a +2. And what I have to do, camera's going crazy. The main thing I have to accomplish here is I have to get the charges equal to 0. Because, as you remember, I said earlier, the number of electrons that are lost from the metal side of the compound have to be the same number that would be gained by the non-metal. All right, so notice those two already balance out to 0. So we don't have to do anything special to them other than write them right next to each other. And this is calcium. And for these 2-element salts like this, binary compounds they call them, you choose the root word for the second element, and the root word for oxygen is ox. Then if there's only 2 elements present, you add I-D-E. Okay. A few minutes ago, okay, so this compound's name, as we know, is sodium chloride, but we write the element that appears first, I'm writing in script here, sodium, and then the root word for chlorine is chlor, and then we stick that, because there's only 2 elements present, a binary compound, sodium chloride, right? Here's my calcium oxide again. All right, let's try another one. Let's go over, don't look too much at these for right now. Let's just go over and look at this column here. And we've got the same problem again. Come on. Let's focus. It's got too many things to focus on, I think. So here we have aluminum, which is +3. And let's use nitrogen, which is right there, which is a -3. So here is aluminum, -3, nitrogen, sorry, aluminum's +3, and nitrogen is -3. And numerically and electrically, we can see that these things balance to 0. Can you figure out what the name of this thing would be? Aluminum nitride. Okay, so the root word for nitrogen is NITR, nitride. Okay, these balance to 0, these balance to 0. Back over here. These balanced to 0. And flipping erases some of it, I see. Could be a problem in the future. All right. So these have worked really nice because we have one atom of each, but sometimes things get a little bit more complicated. For instance, what if we had calcium, which is +2, and chlorine, which is -1? There's a number of ways to do these, but there's a kind of a way that I would suggest you do to start with, and then maybe a way to do after you get the hang of it. But what we're trying to do now is to account for the transfer of electrons, and it has to be the same on both sides of the compound so that the charges cancel to 0. So here we have +2 and -1. And we see that does not cancel to 0. That gives us a +1 total. So here's one way that you can do this to start off with. You can say there's a negative, just let's add another chlorine, and that gives us 2 negative, which over here cancels with +2 to 0. So if we add a chlorine, in other words, calcium is not going to react with one chlorine. It's going to need 2 chlorines to react. So if it has 2 electrons to lose, there has to be a place for 2 electrons to go to. And if one atom can't take both of them, then you have to bring in another atom to take up the slack. And so this compound becomes chlorine, calcium chloride. Okay. Calcium. So you can see the chlorine is the same in every compound. That's its compound name, chloride. All right. So that's one way to do it. Another way to do it, and this may seem easier, is to say, here is a 2 and a 1. What is the lowest common multiple of both of those? And the answer, of course, would be 2. So then you do what you have to do to get this one equal to 2, and you do what you have to do to get this one equal to 2. So fortunately, this one's already equal to 2, and this one, we're going to have 2 of them to equal 2. Okay. And still, there's another way that you can cancel these out, and this way doesn't work every single time. Almost all the time, you can say whatever number that is. So this is going to be a 2, and that's going to be a 1, and you can see calcium chloride ends up with CaCl2, and you don't use 1s in subscripts. And let's make sure we understand what that is. This is called a subscript, because it's written below the symbol, subscript. Okay. Let's go to another one. What if we had had aluminum and chlorine? Well, chlorine's still -1. Aluminum, we saw a few minutes ago, is +3. All right, well, let's see. If we add one more, that gets us to +3 and -2 is +1. So let's add one more. And now we've got a -3 and a positive 3. So aluminum chloride there we go. You're getting good at this, I know. All right, need another board, but I didn't bring one out. Let me see if I can pause this. I'll just go get another one so I can keep all of them. And well, you know, I just stopped. Let me stop it. Nope. Okay, well, I'll just erase this. Now the sodium's no longer there. And let's continue. What if we had, let's choose another element, potassium. You see where potassium is? Potassium's an alkali metal, right? So it's going to act just like sodium does. They're like cousins of each other. And yes, potassium is also explosive, and it's more explosive than sodium. And that's the reason sometimes these columns are called families. They're called groups most of the time, but sometimes they're called families because they have similar characteristics. You have the same color hair as somebody in your family. Potassium has the same charge as sodium. Okay, so here's potassium. I see a mosquito, so perhaps, you know, as the season progresses, being outside might not be the best studio. All right, so here is positive 1 because it's in the same family as sodium. See if I can get this straightened out again. And then what if we put potassium with chlorine? Well, that would be no challenge. But what if we put it with oxygen or something in the same family as oxygen? Sulfur. Okay. See over here, sulfur's in the same family as oxygen. So I'm going to use a -2. Now, see, you've got your periodic table there. Then all you have to do is just glance at it, and you'll see the charge on sulfur. Come on, camera. All right. I think for this, we're going to need another positive charge so that we can balance that out to 0. Positive and -2, K2S. Okay, there's potassium. Okay, potassium sulfide. All right, what about if we had something else in that family, rubidium, same family as potassium and sulfur, potassium and sodium, and we were to put that with something in the same family with nitrogen. Okay, so it's in the nitrogen family. Okay, it's going to be a -3. All right. There we go. I think I know what I've been doing wrong. Something foolish, which I would not reveal. All right. So looks like to balance this out, there we go, positive and negative 3. So this is going to be RB3P. So that's rubidium, phosphide. All right, a couple more here, and then we'll be done with our video. What if things aren't quite so simple? For instance, suppose I had strontium, which is in the same family as calcium and magnesium. What if I had strontium and nitrogen? Well, you could work this out by doing it this way eventually. You keep adding and subtracting formulas until, okay, let me try to do this the right way now. Okay, maybe that'll straighten it out. All right, so you can do, play with the formulas and everything, but in this particular method, the cross multiply type thing works. But you could also do this, and this is the safest way because this works every time. What's the least common multiple for both of those? And the answer, of course, would be 6. So then you do to the formula whatever you have to do to get 6 on both sides. So there's your negative 6. Here's your positive 6. And notice that I've been writing the charges on the other side instead of in front of the number, and that's because this is electrical in nature and not arithmetical. Okay, and a lot of chemists do this, and others do it the other way. So it really doesn't make any difference. But just be aware that you may see it both ways. All right, so this one becomes SR3N2. We name it the same way, doesn't matter how many are there, how many atoms are there. Strontium or strontium. I say strontium. Nitride. There's the IDE, which tells you there's only 2 elements there. Let's go over here and erase this. Notice I have my special eraser here. They come in big rolls that you can buy at places like Sam's. All right. So now what if we had aluminum, which is positive 3, and oxygen, which is negative 2. Well, once again, the easiest way and the safest way to do this, and I put a plus between them that time, not necessary. What we do here is we check for the least common multiple. So once again, least common multiple is 6. So that means we do whatever we have to do to get this equal to 6. This is -3, and this is, I'm sorry, -6, and this is +6. So that cancels to 0. So the formula for aluminum oxide is Al2O3. Aluminum oxide. Okay, aluminum oxide. So we've had a little lesson today in writing formulas. These are the simple formulas. We decided that what was making all of this happen was the fact that we were using the principle of the octet rule, and that atoms are trying to get 8 electrons in their outer shell. We said that the metals transfer electrons over to the nonmetals. And when they transfer electrons, that makes them positive, however many electrons they transfer. All right, and then negative, however many electrons these gain. So we have positive and negative. That makes the whole world go round. And we will post this video. Dr. Fitz and I are both working together on this, and you might see a video with her later. But we are going to work together, and at some point you'll be seeing more videos, and maybe better. After I look at this one, I may make it a little better. But anyway, stay safe, wash your hands, and I don't know how to cut this thing off. I'm going to try to. I'm trying to get the, let's see if I can switch. So in a few seconds, you're not going to see me anymore. There I am. There's my beautiful, I planted that tree several years ago when it was just a baby. That one, the big one. Okay. I just got a message from somebody. Okay, well, here's stop video maybe, stop recording.